Look at Earth from space tonight. The cities burn with pale orange light, stitched across continents like luminous circuitry, proof of something unprecedented. A species so confident in its planet's stability that it builds skyscrapers on coastlines, plants crops across floodplains, and sleeps soundly beneath skies it trusts will remain breathable. From orbit, the oceans shimmer like hammered silver, vast and deliberate in their circulation, carrying heat from the tropics to the poles, with the quiet efficiency of a system that has been doing this reliably for as long as anything alive has known a world. The atmosphere clings to the surface in a thin, luminous shell, almost impossibly delicate, yet holding, always holding. It is easy looking at this to feel that Earth is a place of equilibrium, that the planet we inherited arrived this way, that its temperament is fundamentally benign. That feeling is not entirely wrong. The last 10,000 years have gifted humanity with a climate of remarkable consistency, warm enough for agriculture, stable enough for civilization, varied enough to feel dynamic while remaining, in the deepest sense, controlled. Ice exists, but it knows its place. The great sheets at Greenland and Antarctica sit at the poles, ancient and immense, yet politely removed from the inhabited world. Glaciers carve slowly through mountain ranges. Sea ice advances and retreats with the seasons in a rhythm so dependable it has been woven into the traditions of Arctic cultures for millennia. This is the Earth we know. Tilted at 23 degrees, spinning reliably, breathing carbon in and out through volcanic exhalation and biological absorption, sustaining conditions close enough to constant that a human lifetime feels like geological permanence. But permanence is an illusion that only exists when you are not looking far enough back. Strip away the last 10,000 years. Strip away the last million. Go further. Further than the first hominid, further than the first mammal, further than the first animal complex enough to feel cold. Travel back 700 million years into a chapter of Earth's history so extreme it strains the architecture of modern imagination. You arrive at a world that shares this planet's name and almost none of its character. The continents are alien in their arrangement, clustered differently, wearing no familiar outline. The atmosphere breathes a different mixture. The oceans, for reasons that will take time to unravel, are beginning to behave in ways that no living thing has ever witnessed. Because on this earth, almost nothing yet lives that can witness anything at all. What happens next is not a cold snap. It is not an ice age in the sense we use that phrase today, those cycles of glacial advance and retreat that have shaped the last 2 million years. Dramatic to us but moderate in geological terms. Ice sheets expanding to cover parts of North America and Europe before pulling back. What happens in the Cryogenian period, a name that translates, without exaggeration, as the age of frozen cold, is something categorically different. Ice does not merely expand, it does not push politely southward from the poles and stop at a reasonable latitude. It does not respect the logic of tropical warmth, it conquers. Glaciers advance until they cross the equator. Ice sheets reach sea level at latitudes where today you would find coral reefs and monsoons in the full intensity of equatorial sun. And the oceans, the vast, heat-carrying, civilization-sustaining oceans, may have frozen over entirely from pole to pole, sealing the planet beneath a shell of ice that in some estimates grew to more than a kilometer thick. Not a frozen Arctic, not a cold spell, a world locked. A planet that by any measure we would recognize had nearly ceased to function as a living system. The evidence for this is not theoretical speculation, preserved only in the abstract language of climate modeling. It is physical. It is written in stone, in the literal sense, and geologists have been reading it for decades with growing unease. In places that sit today within the tropics, in what is now Namibia, in Brazil, in parts of Australia, there are ancient rock formations carrying unmistakable signatures of glacial activity. Striations carved by moving ice into bedrock that was once at sea level. Dropstones, boulders so large they could only have been transported by glaciers, suspended in fine sediments that could only have been deposited at the bottom of an open ocean. The two features existing together in the same ancient layer, whispering an impossible combination: ice and open water at the equator simultaneously. The rocks are not ambiguous. The tropics were frozen. Whatever we assume about planetary balance, Earth has already disproved it. This is the paradox that lives inside Snowball Earth. Not merely the cold, but the collision it creates with everything we intuitively believe about how a planet works. We know that sunlight is most intense at the equator. We know that tropical oceans absorb heat and redistribute it globally, keeping the system alive. We assume on some level that these mechanisms are self-correcting, that the planet has guardrails, that even in the extremes of geological history there were limits beyond which the system would not fall. The tropical glaciers say otherwise. They say the guardrails failed. They say the system did not self-correct in time. They say that once enough ice formed, it reflected enough sunlight back into space to cool the planet further, which formed more ice, which reflected more sunlight, a feedback loop with no natural break, accelerating toward total planetary freeze with the cold logic of a runaway equation. If Earth can do that once, the question stops being geological. It becomes something more personal, more vertiginous, more difficult to dismiss before sleep. If this planet, our planet, the one glowing peacefully from orbit tonight, if it can reach a state of near total obliteration and arrive on the other side still capable of hosting life, then what does stability actually mean? What are we trusting when we trust the climate? What exactly is the system we have built every civilization on top of? That question does not have a comfortable answer, and to find even an uncomfortable one, we need to go further back into the conditions that made Snowball Earth not just possible, but, it turns out, almost inevitable. 720 million years ago, Earth is not the planet you would recognize. Stand on its surface, if you could, and the sky above you holds the same sun, slightly younger, burning at perhaps 94% of its current luminosity, close enough to familiar, yet meaningfully cooler in the energy it delivers to a world that, at this moment, urgently needs every fraction of that warmth. The air around you is breathable in composition, though the chemistry of the atmosphere carries different proportions, different pressures, different balances of gases still settling into the long negotiation between rock and ocean and biology that defines a living planet. Beneath your feet, if you could place them anywhere on this earth, the ground would feel recognizable enough. Stone, sediment, the ancient weight of accumulated geology. But look toward the horizon and the geography defeats you entirely. There are no Americas, no Eurasia, no Africa arranged the way you know it. What exists instead is the final, fracturing remnant of something vast. A supercontinent geologists call Rodinia, a name drawn from the Russian word for homeland, which carries in retrospect a quiet irony, because this homeland is in the process of tearing itself apart. Rodinia had been assembling for hundreds of millions of years, continents colliding in slow motion, mountain ranges rising and eroding, land masses fusing into a single enormous entity that at its peak dominated the planet's surface with the authority of something permanent. But permanence, again, is only an illusion that geology hasn't gotten around to dismantling yet. By 720 million years ago, the interior of Rodinia is being pulled apart by the movement of tectonic plates beneath it, rifts opening through the crust, new ocean basins widening between separating landmasses, the supercontinent fragmenting into the scattered pieces that will spend the next several hundred million years drifting toward the configurations we eventually call home. It is one of the most consequential breakups in the history of the planet. Not because of the continental rearrangement itself that is merely geography, but because of what the breakup does to the chemistry of the atmosphere, because of what it exposes, because of what it feeds into a system that is, even now, beginning to lose its balance. When continents rift apart, the process is accompanied by volcanism on a scale that can temporarily warm a planet, injecting carbon dioxide into the atmosphere along the new fracture lines. But the longer, deeper consequence of Rodinia's fragmentation is the exposure of fresh rock, specifically a category of rock that would become the unlikely protagonist of Earth's most catastrophic climate event, silicate rock, the dark iron and magnesium-rich volcanic material called basalt, freshly erupted and freshly exposed along the margins of the fragmenting supercontinent, presented to the atmosphere in enormous quantities, raw and reactive, ready to begin a chemical process that the planet had been using for hundreds of millions of years to regulate its own temperature. That process is silicate weathering. And to understand what is about to go wrong, you first need to understand how elegantly it has been going right. Carbon dioxide in the atmosphere dissolves into rainwater, forming a weak carbonic acid. That acidic rain falls on exposed rock, particularly silicate rock, and reacts with it chemically, breaking down the minerals, drawing the carbon out of the atmosphere, and carrying it dissolved in rivers down to the ocean, where marine organisms incorporate it into calcium carbonate shells that eventually sink to the seafloor, locking the carbon away in deep geological storage for millions of years. When volcanism is high, more carbon dioxide enters the atmosphere. Temperatures rise, more rain falls, weathering accelerates. Carbon is pulled down faster, temperatures stabilize. When volcanism is low, the process slows, carbon accumulates, temperatures hold. It is a thermostat, imperfect, slow, operating on timescales of millions of years, but functional enough to have kept Earth within broadly habitable boundaries across deep time. The planet breathes carbon in through volcanoes and breathes it out through rock, but thermostats have operating ranges. And what Rodinia's fragmentation creates is a condition that pushes the weathering process beyond the range, within which the thermostat can compensate. The newly exposed basaltic rock along Rodinia's rifted margins is exceptionally reactive to chemical weathering, far more so than the older, more chemically stable rocks that had dominated the surface of the assembled supercontinent. And critically, much of this fresh rock is positioned in the tropics, where rainfall is heaviest, temperatures are highest, and chemical reactions proceed fastest. The conditions for accelerated weathering are nearly ideal. Rain falls on fresh basalt. Carbon dioxide is pulled from the atmosphere with unusual efficiency. The chemical reaction that has always been a gentle regulator becomes, under these specific geological circumstances, something closer to a drain. Drawing down atmospheric carbon faster than the planet's volcanic activity can replenish it. The concentration of carbon dioxide in the atmosphere begins to fall. At first, the effect is subtle. Temperatures decline incrementally. The planet cools by fractions of a degree, then, by degrees, gradually crossing thresholds that are invisible in any individual moment, but transformative in aggregate. At the poles, where temperatures are naturally coldest, ice begins to expand. This too is initially unremarkable. Polar ice has expanded and contracted many times in the planet's history in response to orbital variations and atmospheric shifts, and the system has always recovered. The ice forms, reflect some sunlight, and the subtle cooling effect is eventually counteracted by the reduction in weathering that comes with lower temperatures, allowing carbon dioxide to rebuild and warmth to return. The thermostat catches it. The system recovers. This is how it has always worked. Except this time, something is different. This time, the geometry of the continents, the chemistry of the freshly exposed rock, and the position of that rock in the tropical weathering zone combine to create conditions in which the thermostat cannot catch up quickly enough. Ice expands further than it has before. And as it does, it activates a mechanism that the planet has no defense against. A feedback loop that, once engaged at sufficient scale, operates with the indifferent momentum of physics. Ice is white. Oceans and bare rock are dark. Dark surfaces absorb sunlight. White surfaces reflect it back into space. This difference in reflectivity, what scientists call albedo, is not incidental to climate, it is foundational to it. Open ocean absorbs approximately 94% of the solar energy that strikes it. Fresh snow reflects approximately 85% of the same energy back before it can warm anything. When ice covers ocean, it does not merely represent the absence of warmth. It actively returns incoming solar energy to space, preventing it from ever entering the planetary system. The larger the ice sheet, the more energy is reflected. The more energy is reflected, the less warmth the planet retains. The less warmth the planet retains, the further the ice expands. This is the ice albedo feedback loop, and in the circumstances of 720 million years ago, with carbon dioxide already declining and temperatures already falling, it begins to engage not as a temporary fluctuation, but as a self-reinforcing cascade. Ice forms at the poles. Temperatures drop slightly across mid-latitudes. Ice creeps toward lower latitudes. The planetary albedo increases. More energy reflects away. Temperatures drop further. Ice advances again. Each step feeds the next with mechanical inevitability, and crucially, as temperatures drop, the rate of silicate weathering slows. The very process that initially drove the cooling now loses efficiency as rain becomes scarcer and chemical reactions sluggish in colder conditions. The thermostat weakens precisely when the planet needs it most. The carbon dioxide drawdown that began this cascade slows, but not fast enough, and not before the feedback loop has gathered a momentum that carbon dioxide recovery alone may no longer be sufficient to interrupt. Across hundreds of thousands of years, fast in geological time, incomprehensibly slow by any human measure, the world transforms, the oceans cool. The surface waters that once circulated warmth from tropics to poles grow sluggish, their thermal gradient diminishing as high-latitude cooling accelerates, and equatorial warmth begins to ebb. Sea ice forms where there has been no sea ice before. Glaciers descend to lower and lower elevations on land. The ice line, the boundary between frozen and unfrozen surface, migrates steadily toward the equator, not catastrophically in any single moment, but relentlessly over time. Each advance slightly more than the one before, each retreat slightly less complete. Life at this point is mostly microbial. The planet's biosphere in the cryogenian period lacks the complex animals that would later define the fossil record. No fish, no insects, no creatures with enough cognitive architecture to experience what is happening. But life is not absent. Microbial mats coat the shallow seafloor in photosynthetic communities that have been building oxygen into the atmosphere for over 1 billion years. Algae drift in the surface waters, small and biochemically sophisticated, capable of tolerating considerable environmental variation. Stromatolites, layered structures built by communities of bacteria, rise from the seafloor in columns as patient as geology itself, slow-growing monuments to the persistence of early life. These communities are not passive in the climate system. They process carbon, produce oxygen, influence ocean chemistry. They are participants in the planetary negotiation, not merely spectators. But as the oceans cool and the ice advances, the shallow marine environments where photosynthetic life concentrates begin to shrink. Ice covers the surface waters. Light no longer penetrates to communities that have built their entire chemistry around it. The productive zones of the early ocean contract toward the diminishing equatorial regions, compressed between advancing ice fronts from both hemispheres, the living world narrowing along with the temperate band that sustains it. None of this feels yet like catastrophe. The pace is too slow for that word, too geological in its cadence, too remote in its unfolding from anything that maps onto the vocabulary of crisis. It is not a sudden strike from outside the system. It is not an asteroid, not a volcanic supereruption, not a single rupture in the planetary order. It is something in many ways more unsettling. A system behaving exactly as its physics requires, each step following the last with perfect logical consistency. The planet cooling by its own chemical and physical rules, sliding by degrees toward a threshold that, once crossed, will not be a matter of degrees at all. The ice continues its advance. The carbon dioxide continues its slow decline. The feedback loop does not pause, does not reconsider, does not approach the equator with any awareness of what crossing it will mean. It simply moves. And somewhere ahead, closer now than it has ever been, lies a boundary beyond which the thermostat will lose its last remaining leverage. The feedback loop will become irreversible on any timescale that matters, and the planet will tip from a world that is merely cold into something that has no modern analog, no gentle comparison, no way to be described except in terms of total and absolute surrender to ice. What happens when that boundary is crossed is not a continuation of what came before. It is a different category of event entirely. The ice did not stop. That is the fact that separates what happened during the cryogenian period from every other cold episode in Earth's long and varied climate history. Not that ice formed. Ice has formed many times across many eras, in many configurations, and the planet has always absorbed it, metabolized it, recovered. Not that temperatures fell or glaciers advanced, or polar seas thickened with frozen water. All of that has happened before and will happen again without consequence enough to remember. What makes this moment different? What carves it into the geological record with the depth and clarity that 400 million subsequent years of burial and compression and tectonic recycling cannot fully erase, is simpler and more terrible than any complex mechanism. The ice formed, and then it kept moving, past every latitude where physics suggested it should slow, past every threshold where the planetary thermostat should have intervened, past the boundaries that had contained every previous glaciation in the history of the planet. Across the mid-latitudes, down through the subtropics, into the zones of perpetual equatorial sunlight, where no model of a functional climate system predicted ice could survive. It did not merely survive, it accumulated. Somewhere in what will one day become the ancient rock record of southern Africa, in formations that now sit exposed at the surface of a continent that did not yet exist in its current form, the evidence of this crossing is preserved with a precision that geology rarely offers. Glacial striations, parallel grooves cut into bedrock by the grinding advance of ice-laden glaciers moving across stone, are found in rock sequences deposited at sea level in what, during the Cryogenian period, was unambiguously tropical latitude. The striations do not lie. They are not the product of any process other than ice moving across rock under pressure. They require glaciers, and glaciers at sea level in the tropics require a planet that has crossed a line from which, in the logic of the albedo feedback system, there is no ordinary return. The rock was tropical. The ice was real. The two facts sit together in the same stone layer, separated by no gap of time, no intervening period of recovery, just ice at the equator, cutting its signature into the floor of a world that should have been warm. The dropstones tell the same story, from a different angle, in fine-grained, sedimentary sequences deposited in deep, quiet water, the kind of environment where only the smallest particles settle, where nothing coarse arrives except by falling from above. There are boulders, some the size of a human head, some larger, rocks that have no business in these sediments, that could not have arrived by current or by wind or by any mechanism except one. They were frozen into the base of floating ice, carried far from their source as icebergs calved from advancing glaciers and dropped into the deep water as the ice melted beneath them, falling through the fine sediment record. Like stones dropped into still water, landing with a geological thud that 700 million years of subsequent history has not managed to dislodge. Dropstones in tropical deep water sediments, ice floating at the equator. The planet had not merely cooled, it had restructured. To understand what this restructuring meant for the living systems of the early Earth, you have to understand what the oceans were doing, or more precisely what they were ceasing to do. The circulation of the world's oceans is not a passive process. It is driven by differences in temperature and salinity between water masses, by wind stress on the surface, by the geometry of the ocean basins, by the thermal gradient between the sun-heated tropics and the heat-radiating poles. This circulation moves energy. It carries warm surface water poleward and returns cold, nutrient-rich deep water toward the equator, distributing heat from where the planet receives it most intensely to where the planet loses it most readily, moderating both the tropics and the poles, maintaining the temperature gradients that drive weather systems, supporting the biological productivity of surface waters across every latitude. Remove that circulation and you do not simply have a colder ocean. You have a fundamentally different kind of ocean. Stagnant, stratified, unable to equilibrate, extreme at every latitude in ways that an actively circulating ocean smooths away. As the ice advanced through the Cryogenian, the circulation began to fail. The thermal gradient that powered it was collapsing from the pole side inward. Polar waters already locked beneath ice, losing their ability to drive the density-driven overturning that pulled the global system forward. Surface waters at mid-latitudes cooled faster than equatorial waters could compensate. The heat transport that had been moderating polar temperatures, providing the additional warmth that might have slowed the advance of ice, diminished precisely as it was most needed. The oceans were losing their ability to fight back, and as circulation slowed, sea ice thickened, not just at the margins but across vast interior stretches of ocean, growing from a thin seasonal veneer into a permanent, deepening platform of frozen water that sealed the surface from the atmosphere above and the liquid depths below. Light penetration fell. Sea ice, even relatively thin sea ice, dramatically reduces the amount of sunlight that reaches below the surface. The photons that photosynthetic life in the water column depends upon, the energy that drives the biological productivity of the ocean. As the ice thickened across equatorial and mid-latitude oceans, the underwater light environment collapsed. The productive surface layer, already compressed between advancing ice fronts from both hemispheres, shrank to a narrow band at the equator and then narrowed further. The microbial communities that have been building the planet's oxygen budget for over 1 billion years found their access to light physically blocked by the very substance that their planet's chemistry had, by terrible irony, helped to create. Above the ice, the atmosphere was changing with equal consequence. The decline in silicate weathering, now almost entirely suspended across the frozen land masses of the fragmenting Rodinia fragments, where glaciers had replaced the reactive tropical soils with ice, meant that carbon dioxide was no longer being drawn from the atmosphere at the rate that had initially triggered the cooling, but neither was it accumulating fast enough to reverse what had already happened. The volcanic activity that continuously injected carbon dioxide into the atmosphere was still operating, still releasing gas along rift zones and subduction boundaries. But the output was modest compared to the scale of the albedo feedback now dominating the planetary energy budget. Remained in the atmosphere was a fraction of what the planet had relied upon. What remained in the atmosphere was insufficient to trap enough solar energy to compete with the reflective power of an ice sheet that now covered the majority of the planetary surface. The numbers rendered in physical terms are staggering in their finality. A fully ice-covered Earth reflects approximately 60 to 70% of all incoming solar radiation back into space before it can warm anything. The planet's energy balance, the relationship between incoming sunlight and outgoing heat, which must remain roughly equal for surface temperature to stay constant, tips catastrophically toward the outgoing side. The planet radiates more energy than it receives. It cools further. The ice that is causing the reflection grows thicker in response. The reflectivity increases again. There is no mechanism within the ice albedo feedback loop itself that arrests this process. No internal thermostat, no self-correcting chemistry operating on a timescale fast enough to intervene once the system has passed the critical threshold. The feedback does not know what a tipping point is. It does not slow at the equator out of recognition that it has gone too far. It simply continues because physics does not negotiate with consequences. The world dims. This is not metaphor. It is the literal optical reality of a frozen planet. The brilliant blue of open ocean, which from space had made this world glow with a particular luminous depth, bleaches out beneath expanding ice. The dark equatorial land surfaces that absorbed sunlight and radiated warmth back into the overlying atmosphere are buried. The planet's face, seen from space, grows progressively whiter, brighter, colder, a mirror where there was once an absorber, reflecting back into the void the very energy that might have saved it. The sun still shines. The light still arrives across 93 million miles of space with the same intensity it has always delivered. But the planet is no longer receiving it in any meaningful sense. It is deflecting it, sending it back unused, like a body that has lost the capacity to metabolize food, surrounded by energy, starving of warmth. Beneath the growing ice sheets on what were once equatorial landmasses, rock that had spent millions of years in chemical conversation with the atmosphere is entombed. The weathering reactions cease. The carbonic acid rain that dissolved silicate minerals and drew carbon from the air no longer reaches the reactive surfaces beneath glacial ice. The ice itself forms a physical barrier between the chemistry of weathering and the minerals it requires. Carbon dioxide continues to be exhaled by the planet's volcanic systems, but with the atmospheric drawdown engine shut down by ice cover, the gas that builds is insufficient to compensate for the catastrophic heat loss from the runaway albedo feedback. The atmospheric greenhouse weakens further. Temperatures at the equator, once stable near 25 degrees Celsius, collapse through zero, through -10, through temperatures that, in any subsequent era of Earth's history, would be associated only with the interior of Antarctica in the depths of polar winter. For the microbial life still persisting in the narrowing refugia of open water, in the hydrothermal communities around seafloor vents, in the thin films of liquid brine that can persist within ice at temperatures well below freezing due to salt concentration, the world has become something close to the boundary of what chemistry allows. Life at this scale is resilient in ways that larger organisms cannot approach. Individual microbes do not experience cold the way a body does, do not shiver or seek shelter, simply slow their metabolic processes to rates that match the energy available to them, persisting at the threshold between active life and suspended animation. But the communities that once spanned vast productive ocean surfaces are fragments of themselves. The biosphere of Earth in the depths of snowball glaciation is not extinct, but it has been compressed, isolated, reduced to scattered outposts in a frozen world, clinging to the last sources of liquid water and chemical energy in a planet that has, in almost every physical sense, closed for business. The oceans beneath the ice are not dead. Liquid water, kept from complete freezing by the residual heat of the planet's interior, and the insulating properties of the ice itself, still moves in sluggish darkness beneath a ceiling of frozen ocean. Chemical reactions still proceed on the seafloor, slow and cold, maintaining the faint biochemical hum of a biosphere that has not yet surrendered. But the surface world, the zone of sunlight and photosynthesis and atmospheric exchange that had defined productive life for 1 billion years, is sealed, silent, white. Earth has become something it has never been before, and will never be again in quite this form. A frozen shell around a barely living interior, a planet that has swallowed its own warmth and locked it away beneath ice kilometers deep. The cascade that began with chemistry, with rain on a fresh rock, with carbon dioxide drawn patiently from an atmosphere, has completed itself in a transformation so total that the word climate no longer seems adequate. This is not a climate, this is a sentence. But deep inside the planet, something has not stopped. Something slow and pressurized and indifferent to the ice above it is still building. And it will not build forever. What does a frozen ocean sound like? Not the creak and groan of sea ice at the poles, the familiar noise of a world that is cold at its edges but alive at its center. That sound belongs to a different planet, a more forgiving one. This is something else. This is the sound of an ocean that has surrendered its surface entirely, ice thickening not by centimeters but by meters, then by tens of meters, then by hundreds, pressing down on the water below with a weight that silences everything it touches. In the depths of the cryogenian glaciation, at the moment the planet crosses from severe cold into something that has no name in the vocabulary of the world we know, the oceans do not merely freeze at their edges, they seal. And the silence that follows is not the absence of sound so much as the presence of something total. A planetary quiet that has no modern analog, no living witness, no frame of reference except the rock that recorded it and the science that learned, slowly and with considerable disbelief, to read what the rock was saying. From space, the transformation is absolute. The Earth that glowed blue and white and brown and green in the preceding hundreds of millions of years, a world whose colors were the colors of chemistry and biology and the particular way liquid water handles light, has become something that resembles none of those things. What hangs in space now is white, almost uniformly, almost completely white. The brilliant reflective surface of a planet encased in ice stretches from pole to pole without meaningful interruption, broken only by the exposed peaks of the highest mountain ranges, the dark lines of active volcanic chains still exhaling heat along rift zones, and the thinnest possible remnant of open or semi-frozen water near the equator, where the geometry of solar input still marginally exceeds the rate at which the surface can freeze. From the distance of the moon, this planet does not look like Earth. It looks like a pale sphere of reflected light, a mirror held up to the sun, a world that has turned its face away from warmth and has nothing left to show the universe but ice. The temperature at the equatorial surface has fallen to somewhere between -20 and -50 degrees Celsius, depending on the model and the specific phase of the glaciation. These are not temperatures that exist anywhere on the modern Earth's surface, except in the most extreme interior conditions of the Antarctic plateau in the depths of austral winter. And even there they are seasonal, temporary, moderated by the knowledge that the sun will return with more authority in a matter of months. Here at the equator of a frozen world, they are permanent. The sun rises and sets with the same mechanical regularity it always has, delivering its light to a surface that returns 90% of it to space before it can convert to heat. A transaction so one-sided that the difference between night and equatorial day is reduced to a fraction of what it was before the freeze. The sun shines on a world that no longer knows how to be warmed by it. Beneath the ice, the oceans exist in a state that strains the meaning of the word ocean. Liquid water is still there. The planet's interior heat, the slow radioactive decay in the mantle and crust that has been warming Earth from within since its formation, continues to flow upward through the seafloor, maintaining a temperature differential sufficient to keep the deep ocean from freezing solid. The ice above is thick. In some regions, modeling suggests it may have grown to 1 kilometer or more, a frozen ceiling pressing down on the water below with the weight of a small mountain range per square meter. But it is not infinite, and the heat from below maintains a liquid interior even as the surface is locked. This is not comfort, it is a technicality. The ocean beneath a kilometer of ice is dark in a way that light has never been dark before in this planet. Pressure crushed, chemically isolated from the atmosphere above, cut off from the photosynthetic cycle that had been producing oxygen and organic carbon, for over 1 billion years. The collapse of photosynthesis in the surface ocean is not an event. It is a process, drawn out over the hundreds of thousands of years of the advancing freeze, each stage more complete than the last, the productive zone of the water column shrinking and dimming and finally disappearing beneath ice that admits no light at all. Cyanobacteria, the ancient photosynthetic microbes that had been oxygenating Earth's atmosphere since well before the cryogenian, require light. They are not obligate. Some can switch to alternative metabolic strategies under extreme conditions. But the community-scale productivity that built the oxygen atmosphere depends on photons reaching cells that can use them. When the ice seals the surface, the photons stop. The productivity stops. The oxygen production that life had been investing in for over 1 billion years, the slow, patient work of converting sunlight and carbon dioxide and water into organic matter and atmospheric oxygen, largely ceases at the surface of a frozen world. What persists is not nothing, and this matters enormously to the story that comes after. The hydrothermal vent communities along the mid-ocean ridges, those strange chemically powered ecosystems clustered around the fissures where the planet bleeds heat and mineral-rich fluid into the cold abyssal water, continue operating with the biological indifference to surface conditions that is, in retrospect, one of the most significant facts in the history of life. These communities do not depend on sunlight. They are powered by chemical energy, by the oxidation of hydrogen sulfide and methane, and other reduced compounds exhaled from the interior of a geologically active planet. They existed before the freeze. They persist through it. And in the complete absence of light-powered productivity everywhere else, they become the primary refuge of complex microbial life. Isolated outposts in the darkness beneath a frozen ocean, maintaining the thread of biological continuity that will, millions of years later, prove to have been sufficient. In the shallower regions where ice meets seafloor, the continental shelves of the cryogenian world, now buried under glacial ice that extends to sea level and below, a different kind of extreme persistence operates. Thin films of liquid brine, maintained against freezing by their salt concentration, persist within the ice matrix itself. And in these microscopic channels, microbial life continues at metabolic rates so reduced they barely qualify as living by any energetic definition. This is not thriving, it is barely surviving. Life reduced to its absolute minimum expression, processing energy at rates that would take geological eons to accomplish anything measurable, sustained by the one property that distinguishes even the simplest living chemistry from the inert world around it: the capacity to keep going when everything in the environment argues for stopping. Meanwhile, the planet's geological machinery has not paused for the ice above it. Volcanoes do not consult the climate before erupting. The tectonic forces that drive volcanism, the convection of the mantle, the subduction of oceanic crust, the rifting of continental fragments, operate on time scales and energy scales that make the surface temperature of the planet irrelevant. Along the active volcanic arcs and rift zones of the cryogenian world, eruptions continue with the same statistical regularity they have always maintained, injecting carbon dioxide into the atmosphere at the same average rate, adding greenhouse gas to a sky that is, under any normal set of planetary conditions, designed to trap that heat and warm the surface. Under normal conditions, this volcanic outgassing is the other half of the carbon cycle's thermostat. When weathering draws carbon down too far, volcanic replacement eventually rebuilds it. Temperatures recover, balance restores. The thermostat turns the heat back on, but the thermostat requires a surface capable of responding to greenhouse warming. And what the ice has created is a surface that cannot. The ice reflects incoming solar radiation with such efficiency that additional greenhouse gas in the atmosphere produces far less warming than it would over a dark ocean or vegetated land. The radiative physics of a high albedo surface breaks the relationship between carbon dioxide concentration and surface temperature that normally governs planetary climate. Carbon dioxide builds in the atmosphere, slowly because volcanic outgassing is a patient process, measured in parts per million over millions of years. But the warming that should follow from its accumulation is suppressed by the reflective barrier of the ice itself. The planet holds the heat below the ice, loses it above, and sits in a frozen stasis that its own chemistry is slowly, almost imperceptibly, working to undermine, but not yet, not for a very long time yet, succeeding. The atmosphere of the white planet is alien in ways beyond its temperature. The oxygen content, which had been building steadily for hundreds of millions of years through biological photosynthesis, is no longer being actively replenished at the surface. The chemical reactions that consume oxygen, oxidation of exposed minerals, reaction with volcanic gases, the metabolic processes of whatever microbial life persists, continue drawing it down without the photosynthetic renewal that previously balanced the budget. The atmospheric chemistry shifts slowly toward a composition that reflects the dominance of geological over biological processes, the planet expressing itself through its rock rather than its life, carbon dioxide building in the upper atmosphere while oxygen gently declines, the two great chemical signatures of a living planet moving in the direction of a world that is reverting to something older and less biological. On the surface of the ice, nothing moves. This needs to be held in the mind not as metaphor or exaggeration, but as physical description. There is no wind-driven transport of organic material across a landscape of life. There are no tidal pools hosting photosynthetic communities at the margins of a cold sea. There are no shallow bays where cyanobacterial mats carpet the sediment in the greenish-black evidence of biological productivity. The land surface of the equatorial regions, once washed by warm tropical rain, that drove the silicate weathering responsible for starting this entire cascade, is buried under glacial ice that has ground the bedrock flat and sealed it from every chemical and biological process that rain enables. The rock weathers no further. The carbon drawdown has stopped completely. The landscape is static in the way that only an ice-covered landscape can be. Not the static of a desert, where wind still moves sand and temperature still cycles between night and day with enough amplitude to crack rock, but the static of entombment, where the surface has been removed from the active world entirely and placed in geological storage. This is what it means for a planet to become a snowball. Not cold, not glaciated, but removed from itself. Its chemistry suspended, its biology contracted to the margins, its surface decoupled from the atmospheric processes that normally define a living world. Earth, in the depth of the cryogenian glaciation, is not a planet that is suffering. It has no capacity for that. It is a planet that has been reorganized by physics into a configuration that is self-sustaining in its extremity, that requires no further forcing to maintain, that will persist in this state not for years or decades or centuries, but for millions of years, held in frozen stasis by the same feedback loop that drove it here. The albedo of its own ice surface deflecting the solar energy that is the only force available to break the cycle from outside. Millions of years. The number does not translate easily into meaning. A million years before tonight, the first members of the genus Homo were still hundreds of thousands of years from existing. 10 million years ago, the ancestors of humans had not yet diverged from the ancestors of chimpanzees. 700 million years ago, the entirety of complex animal life that has ever lived, the Cambrian explosion and everything that followed, was still more than 100 million years in the future, waiting on the other side of a frozen epoch that must first be survived. The white planet does not know any of this. It simply is. Frozen, silent, white, reflecting light into space with the serene indifference of a system in equilibrium, holding the last remnants of life in chemical suspension in the darkness beneath its ice, waiting for a force sufficient to break it. Deep in the mantle, the convection currents that move tectonic plates are still moving. Magma is still rising. Carbon dioxide is still, molecule by molecule, year by year, adding itself to the frozen planet's atmosphere. The concentration is climbing toward a threshold that cannot be crossed without consequence, building the way pressure builds behind a sealed valve. Slowly, invisibly, and with an eventual release proportional to every million years of accumulation. The ice holds, but not everything beneath it is still. Nothing survived on the surface, but something endured. That distinction just between surviving and enduring is the one is not semantic. It is the difference between life as we prefer to imagine it, robust and visible and generative, spreading across sunlit surfaces with the confident biology of a world in its prime, and life as it actually is at its core. A chemical stubbornness so fundamental that it persists not because conditions permit it, but because the threshold required to eliminate it entirely is higher than even a frozen planet can reach. On the surface of the white planet, in the conventional sense of the word surface, the ice, the frozen ocean, the glaciated land masses, the dim equatorial zones where sunlight arrives and reflects away without warming anything. Nothing survived. No community. No ecosystem. No biological process operating at a scale that the word life comfortably describes. The surface was vacant in a way that no subsequent era of Earth history has replicated, a biological silence so complete that the planet's own geological processes, the volcanism and tectonic movement and chemical cycling that continue regardless of biology, dominated the planetary story entirely. Beneath that surface, in the dark and the pressure and the chemical margins of a world that had sealed itself from the sky, something endured. And the story of that endurance is, depending on how you choose to measure significance, the most important biological story in the history of this planet. The hydrothermal vent systems of the cryogenian seafloor were not refuges in any comfortable sense of the word. They were not warm pockets of preserved normalcy, sheltered islands of the previous world maintaining themselves in miniature while catastrophe raged above. They were extreme environments under ordinary conditions, superheated, chemically saturated, pressurized, and the freezing of the planet above them changed their character without softening it. What they offered was not comfort but chemistry. The continuous outflow of reduced chemical compounds from the planet's interior, hydrogen sulfide, methane, molecular hydrogen, dissolved metals, the raw material for a metabolic strategy called chemolithotrophy, the extraction of energy from the oxidation of inorganic compounds rather than from sunlight. For the microbial communities that had evolved in this environment long before the cryogenian, the freeze changed nothing essential. The energy source was geological, not solar. The surface was irrelevant. The ice kilometers above was to a microbe living at a hydrothermal vent on the abyssal sea floor, simply another feature of a universe that had always been defined by pressure, heat, and chemistry rather than light. These communities were not diverse in the way that surface ecosystems had been diverse. The biological richness of the shallow marine environments, the variety of metabolic strategies, the complex interactions between photosynthetic producers and the communities that fed on their output, the chemical stratification of oxygenated surface water overlying the deeper anoxic zones. That richness was gone, sealed under ice, contracted to nothing. What remained at the vents was functionally narrower, dominated by organisms built for extremity, capable of metabolizing compounds that most life would find toxic, operating at temperatures and pressures that define the outer boundary of what biochemistry can sustain. By any ecological metric applied to the world before the freeze, these communities were impoverished. By the only metric that matters in the context of a global glaciation, they were sufficient. They were alive. They were reproducing, however slowly. They were maintaining the molecular machinery of life through millions of years of planetary winter. In the thin melt zones near the equator, where the geometry of solar input and the thermal properties of the ice created conditions marginally above absolute biological minimum, a different category of persistence operated. Liquid water, the irreducible requirement for life as Earth has always expressed it, existed in pockets and films and channels within the ice matrix. Cryoconite holes, brine channels, the interface between ice and underlying rock where geothermal heat was sufficient to maintain a microscopic liquid layer. In these spaces, measured in millimeters rather than kilometers, microbial communities clung to existence with a metabolic minimalism that approaches the definition of life from its lower boundary. Photosynthetic microbes in surface ice could, under certain conditions, access the diffuse light filtering through thin ice cover, driving photosynthesis at rates so reduced that the term barely applies, but sufficient to maintain cellular integrity and, crucially, to reproduce across geological time. A generation time that stretches from days to months under these conditions still produces enough generations across 10 million years to matter evolutionarily. Slow is not the same as stopped. Marginal is not the same as extinct. The subglacial oceans, the liquid water maintained beneath the ice by interior planetary heat, offered a third category of refuge, perhaps the most volumetrically significant in terms of the sheer amount of liquid water preserved. Beneath ice sheets kilometers thick, in contact with the seafloor and the chemical inputs of ongoing geological activity, an ocean persisted in darkness so complete that no photon of solar origin could reach it. The biology sustained here was entirely decoupled from the sun, dependent instead on the chemical energy of water rock interactions, on the slow release of hydrogen from the serpentinization of seafloor basalt, on the metabolic cycling of whatever organic carbon had been deposited before the freeze and was now being slowly recycled in the cold dark. This is not an ecosystem in any conventional sense. It is a system, a slow, chemically driven cycling of the basic ingredients of life through communities of organisms that have reduced their requirements to the absolute minimum compatible with continued existence. But it is continuous. It persists through millions of years of glaciation without interruption. And continuity across deep time is everything. What these survival niches share beyond the obvious necessity of liquid water is the extreme pressure they exerted on the populations sheltering within them. Evolutionary biology has a framework for understanding what happens to populations when their numbers collapse and their geographic range contracts to isolated refugia. The framework of the bottleneck, the population genetic consequence of severe reduction, followed by eventual recovery. When a population shrinks dramatically, the genetic diversity it carries shrinks with it. The variants, the mutations, the accumulated genetic experimentation of millions of years of evolution are not distributed evenly across individuals. When most individuals die, most variants die with them. What survives is a genetic sample of the previous diversity, partial, unrepresentative, shaped by the accident of which individuals happen to be in which refugia when the contraction happened, rather than by any logic of fitness or optimization. The survivors are not the best. They are simply the ones that were in the right place. Genetic evidence from the molecular clocks embedded in the DNA of living organisms. The accumulated mutations in conserved gene sequences that tick at roughly predictable rates across geological time suggests that the ancestors of many major lineages of life passed through severe bottlenecks in the period corresponding to the cryogenian glaciations. The molecular signatures of dramatic population reductions, of genetic diversity narrowing to a thread, and then slowly expanding again as populations recovered, appear in lineages ranging from algae to the ancestors of animals. This is not proof that Snowball Earth caused these bottlenecks. The molecular clocks carry wide uncertainties, and the precise timing of evolutionary events hundreds of millions of years in the past is not the kind of claim that genomics can make with precision. But it is consistent with the picture painted by geology, that the cryogenian was a period in which the living world contracted to its margins and passed through a filter from which only the most resilient, the most adaptable, or simply the most fortunately positioned lineages emerged. That filter may have done something that pure catastrophe rarely accomplishes. It may have built something. The hypothesis is contentious, and the caution appropriate to any claim that converts mass near extinction into a narrative of productive necessity should be applied generously. But the timing is suggestive in a way that serious scientists have not been able to dismiss. The cryogenian period ends approximately 635 million years ago, with the deglaciation that this section is building toward. And in the geological period immediately following, like the Ediacaran, the fossil record begins to show something that it has never clearly shown before: the first evidence of multicellular animal life. Not microbes organized loosely in communities, not stromatolite structures built by biofilms, but genuinely complex organisms with differentiated tissues, organized body plans, and the biological architecture that distinguishes animals from the microbial life that had dominated Earth for the preceding 3 billion years. The Cambrian explosion, the great diversification of animal phyla that fills the early Paleozoic fossil record, with the ancestors of virtually every body plan alive today, follows the cryogenian by approximately 100 million years. In the context of a planet 4.5 billion years old, that is a tight sequence. One interpretation, not universally accepted but seriously considered, is that Snowball Earth reorganized the biosphere in ways that created evolutionary opportunity. By eliminating the dominant surface ecosystems, the vast, productive, stable microbial communities that had occupied every available ecological niche for 3 billion years, the glaciation may have cleared ecological space in a way that permitted, upon recovery, the rapid exploration of new strategies. By forcing surviving populations through genetic bottlenecks, it may have shuffled the evolutionary deck, concentrating and recombining genetic variants that had previously been diluted across enormous populations. By alternating between extreme cold and, as we will see, extreme heat during deglaciation, it may have applied selective pressures intense enough to accelerate the rate at which novel biological solutions were tested and either eliminated or preserved. Not progress. Evolution has no direction, but acceleration. Disruption creating opening. The worst thing that had ever happened to life on Earth, possibly building the preconditions for the most productive diversification in the history of life on Earth. None of this was legible in the refugia. The microbes at the hydrothermal vents were not preparing for the Cambrian. The brine channel communities in equatorial ice were not banking genetic diversity against future use. Life does not plan. It simply persists with a tenacity that does not require intention to be remarkable. It persists in the dark beneath a frozen ocean, in the scalding outflow of a seafloor vent, in a millimeter-thick film of liquid water between ice and rock, reducing its requirements to the minimum, slowing its metabolism to match available energy, passing its molecular information forward through reproduction at whatever rate conditions permit, holding the thread. For millions of years, in the silence of a frozen planet, the thread holds. And above the ice, invisible to everything living beneath it, the atmosphere continues to change. The thaw did not arrive gently. Nothing about the sequence of events that ended the cryogenian glaciation resembles the word gentle. Not the mechanism that triggered it, not the rate at which it unfolded, not the conditions it created on the other side, not the chemical violence it unleashed on oceans that had been sealed and silent for millions of years. The end of Snowball Earth is not a story of gradual recovery, of temperatures creeping incrementally back toward habitable, of ice retreating in the orderly reverse of its advance. It is a story of a planetary system that had been absorbing pressure for tens of millions of years, finally crossing a threshold beyond which the pressure releases all at once. Not the controlled release of a system returning to equilibrium, but the explosive release of a system that has been storing energy in one form and converts it, in geological terms almost instantaneously, into something else entirely. The planet did not thaw, it detonated. The mechanism had been building since the first year of the freeze, patient and invisible and entirely indifferent to the ice accumulating above it. Volcanoes do not stop for glaciations. The tectonic forces driving volcanic activity operate on energy scales that make surface temperature irrelevant, and throughout the entire duration of the cryogenian glaciation, across the 10, 20, perhaps 30 million years of maximum ice cover, depending on which geological interpretation you accept, the planet's volcanic systems continued exhaling carbon dioxide into the atmosphere at their baseline rate. Not dramatically. Not in pulses sufficient to overwhelm the albedo feedback in any given millennium. Would be extraordinary in any subsequent era of Earth's history? Past levels that in later geological periods would constitute a climate emergency of global consequence, and continuing to climb because the ice cover that was preventing the warming, these concentrations should have produced was also preventing the weathering reactions that would normally draw the excess carbon back down. The container was sealing tighter as it filled. Carbon dioxide concentrations during the peak of Snowball Earth's volcanic accumulation may have reached values hundreds of times higher than pre-industrial modern levels. Some estimates place the figure at 300 to 400 times the carbon dioxide concentration that existed before the freeze began. These are numbers that, applied to a planet with normal albedo, would produce surface temperatures incompatible with liquid water in the opposite direction. A runaway greenhouse scenario rather than a runaway ice scenario. But the ice was still reflecting. The albedo feedback that had locked the planet into its frozen state was still operating. The greenhouse warming that should have followed from such extreme carbon dioxide accumulation was being partially suppressed by the very surface it needed to melt. The pressure built. The ice held. The gap between what the atmosphere was capable of delivering in terms of warming and what the surface was permitting continued to widen. Tension accumulating in the system with the mathematical certainty of a physical process that cannot go on indefinitely. The threshold, when the planet finally reached it, was crossed not because the ice weakened, but because the greenhouse forcing eventually became sufficient to overcome it at the margins. Near the equator, where the solar input was highest and the ice thinnest, the accumulated warming from centuries of extreme greenhouse concentration began to outpace the reflective cooling from the surface beneath. A narrow zone of melt opened. Dark ocean surface was exposed. That dark surface absorbed sunlight instead of reflecting it. Local temperatures climbed, the melt zone widened, more dark surface was exposed. The albedo feedback that had sustained the freeze for millions of years did not simply slow. It reversed. The same mechanism that had accelerated the advance of ice now accelerated its retreat. Each meter of dark ocean uncovered absorbed more energy. Each degree of warming melted more ice. Each expansion of open water reduced the planetary albedo further. The runaway equation that had frozen the planet ran in the opposite direction with equal and opposite force. The thaw, once initiated, was catastrophic in its speed. Geological evidence from the rock sequences immediately above the cryogenian glacial deposits. The boundary where frozen world sediments give way to the warm world sediments of the post-glacial Ediacaran shows a transition so compressed in time that the word rapid barely captures its violence. What had taken millions of years to freeze may have thawed in thousands, perhaps in less. The ice sheets that covered the continents collapsed under warming that exceeded anything the planet had experienced in the preceding hundreds of millions of years. The sea ice that had sealed the oceans retreated across degrees of latitude in intervals too brief to measure precisely with the tools geology provides, but clearly brief in the way that only catastrophic transitions are brief in the deep time record. The planet swung from a state that had been extraordinarily stable in its extreme cold to a state of extreme heat with a speed that no biological system, no ocean circulation pattern, no atmospheric chemistry could track or accommodate. The surface temperature the planet reached on the other side of the thaw was not the moderate warmth of the world before the freeze. The carbon dioxide that had accumulated across tens of millions of years of volcanic outgassing did not disappear when the ice retreated. It remained in the atmosphere, fully active now that the high albedo surface it had been partially suppressed by was gone, driving greenhouse warming against dark open ocean and exposed land with nothing to counteract it. The planet did not return to its pre-glacial climate. It overshot it dramatically, entering what paleoclimatologists call a super greenhouse state. A period of extreme warmth driven by carbon dioxide concentrations so far beyond any subsequent norm that the surface temperatures they produced were, in some estimates, 10 to 30 degrees Celsius above the modern global average. A world that had been 50 degrees below modern equatorial temperatures swung, in geological terms, almost simultaneously to temperatures that exceeded them by a comparable margin in the opposite direction. The hydrological cycle, reactivated by this extreme warmth, did not resume quietly. Water evaporates faster in warmer air. Warmer air holds more moisture. More moisture means more precipitation. And more precipitation, falling on a planet where the carbon dioxide concentration in the atmosphere had dissolved into rainwater to form carbonic acid of extraordinary concentration, meant acid rain on a planetary scale, not the mild anthropogenic acidification of modern industrial pollution, but genuine chemical assault. Rainfall so enriched with dissolved carbon dioxide that it attacked exposed rock surfaces with a weathering intensity that the planet had never experienced. The silicate rocks freshly exposed by retreating glaciers, the same basaltic formations that had driven the original cooling through their reactivity to chemical weathering, were now subjected to the most aggressive weathering conditions in Earth's history. The carbon drawdown that began this entire sequence, the gentle planetary thermostat that had pulled a little too hard, now operated in reverse at maximum intensity, the super greenhouse atmosphere being dismantled by the very chemistry that had accidentally created it. The oceans, unsealed after millions of years of isolation beneath ice, received the runoff from this chemical assault in a form that their accumulated chemistry was not prepared to handle. Rivers swollen by the extreme precipitation of a hyper-warm planet carried dissolved minerals from freshly weathered rock into ocean basins that had spent millions of years developing their own chemical equilibrium in sealed darkness. The mixing was violent in chemical terms. Calcium ions flooding in from the weathering of carbonate rocks, alkalinity shifting rapidly, the ocean's acid-base balance lurching through transitions that would, in slower circumstances, have taken millions of years to play out. The evidence of this chemical violence is preserved in the rock record immediately above the glacial deposits as cap carbonates. Distinctive layers of calcium carbonate rock that precipitated rapidly from ocean water supersaturated with dissolved carbonate minerals, a kind of geological exhale. The ocean releasing the chemical tension of the transition in a massive precipitation event that left a sharp, bright layer in the stratigraphic record that geologists worldwide can identify as the signature of Snowball Earth's end. The storms that moved across the surface of this post-glacial world were not storms in any scale familiar to a civilization that measures weather in days and seasons. A super greenhouse atmosphere with extreme moisture content and an ocean surface warming at a rate that outpaced atmospheric equilibration generated atmospheric instability at a planetary scale. Convective systems drawing energy from the thermal differential between the still cold deep ocean, upwelling into the rapidly warming surface layer. Moisture cycling through the atmosphere at rates that dwarfed anything in the subsequent geological record. The first life to emerge from the refugia into this recovering world did not step into paradise. It stepped into a planet that had traded one form of uninhabitable extremity for another. The silence of absolute cold, replaced by the chemical aggression and meteorological violence of absolute heat. But the silicate weathering thermostat, running now at maximum efficiency under the combination of extreme warmth, extreme rainfall, and freshly exposed reactive rock, was doing what it had always been designed to do. Carbon dioxide was being drawn from the atmosphere and locked into rock. The concentration was declining. Temperatures were falling back from their post-glacial peak. The super greenhouse was dismantling itself through its own chemistry, the planet overcorrecting in warmth as it had overcorrected in cold, oscillating toward a new equilibrium that was neither frozen nor superheated, but somewhere between. A world recovering its balance after the most extreme climate excursion it had ever endured. The ice was gone, the silence was gone. The life that had waited in the dark beneath the frozen ocean was moving slowly into a world that had been emptied and refilled and reorganized by 60 million years of planetary extremity. It was not the same world. The chemistry was different. The ocean's circulation was different. The atmospheric composition was on a new trajectory. And the life itself, having passed through the filter of the most severe bottleneck in the history of complex biology, was carrying something different in its genetics. A compressed, reshuffled, pressure-tested inheritance that the next 100 million years would begin, slowly and then explosively, to unfold. For the first time in tens of millions of years, sunlight touched open water. Not the diffuse, filtered suggestion of light penetrating thin ice at the margins of a melt zone, not the pale illumination reaching brine channels within a frozen surface, but direct unobstructed sunlight meeting liquid ocean in the full, photochemical transaction that had defined the productive surface of this planet for over 1 billion years before the freeze. The photons that had been arriving with mechanical regularity throughout the entire glaciation, only to be turned away by an ice surface that had no use for them, now entered the water column and began doing what sunlight does when it meets ocean, warming it, driving evaporation, initiating the thermal stratification that structures marine ecosystems, and feeding through the ancient alchemy of photosynthesis the organisms that had survived the long darkness and were now, cautiously, beginning to expand into a world that had been emptied and was, for the first time in geological memory, open. The ocean that received that sunlight was not the ocean that had existed before the freeze. It had spent tens of millions of years in sealed isolation, its chemistry evolving under conditions of darkness and limited biological activity, its dissolved gas concentrations drifting far from the values that the productive surface ecosystems of the pre-glacial world had maintained. Oxygen levels in the deep water had declined dramatically during the glaciation, consumed by chemical reactions with the seafloor and by the slow metabolic activity of surviving microbial communities without being replenished by the photosynthetic production that had previously kept pace. Iron and other nutrients that are normally cycled through the water column by biological activity had accumulated in the deep, released from seafloor sediments into water that lacked the organisms to process them. The post-glacial ocean was chemically primed in a way that the pre-glacial ocean had not been. Rich in nutrients that photosynthetic life requires, saturated with the dissolved minerals that biological productivity consumes, waiting for the return of light and the organisms that could use it. The return, when it came, was not instantaneous. Biology does not fill ecological space the way water fills a container, all at once and indifferently. It expands through reproduction, through the generational accumulation of population growth, through the gradual recolonization of environments by organisms that must find their way there and establish themselves before they can expand further. The survivors from the hydrothermal vent communities, from the brine channels, from the thin equatorial melt zones, began moving into newly available shallow marine environments over thousands of generations, each population growing slowly larger, each expanding community creating the chemical and ecological conditions that permitted the next community to follow. Photosynthesis resumed in the surface ocean. Oxygen began accumulating again in the water column and atmosphere. The nutrient cycles that had been disrupted by millions of years of glaciation began re-establishing themselves as biological productivity returned, and organisms began processing the chemical richness of the post-glacial ocean with increasing efficiency. The reoxygenation was not merely a return to previous conditions. The evidence preserved in the rock record suggests that the post-snowball ocean experienced pulses of oxygenation that exceeded pre-glacial levels. The combination of biological productivity returning to a nutrient-rich ocean and the atmospheric oxygen buildup from photosynthesis, driving dissolved oxygen concentrations in shallow marine environments to levels that the world had not previously sustained for extended periods. Oxygen is not merely breathable, it is chemically reactive in ways that restructure the possibilities available to biological systems. Higher oxygen concentrations in seawater change the redox chemistry of the ocean, alter the stability of organic molecules, affect the metabolic efficiency of organisms that can utilize it, and create selective pressure for biological strategies that exploit its availability. A more oxygenated ocean is a chemically different environment in ways that cascade through every level of biological organization. It is in this context, an ocean reoxygenating, nutrient cycles resetting, ecological space emptied by the most severe biological contraction in the history of complex life, and now refilling from the surviving thread of lineages that had passed through the cryogenian filter, that the Ediacaran biota appears in the fossil record. Strange soft-bodied organisms, unlike anything preserved in the preceding 3 billion years of life's history, quilted frond-like creatures anchor to the seafloor, disc-shaped organisms whose relationship to any living animal remains debated. The first genuinely complex multicellular life whose fossils are unambiguous enough to photograph and hold and wonder at. They appear approximately 30 to 40 million years after the last Snowball Earth glaciation ends, in rock sequences deposited in the shallow seas of a world that was still chemically unsettled but biologically expanding. They are not the ancestors of all subsequent animal life. Many Ediacaran lineages appear to have left no descendants, but their existence marks the moment when the trajectory of life on Earth shifted irrevocably toward the complexity that would, within another 100 million years, produce the Cambrian explosion and every animal body plan that has ever lived. Whether Snowball Earth caused this trajectory shift or merely preceded it remains genuinely open in the scientific literature, and the honesty appropriate to the question requires acknowledging that correlation across geological time is not causation, and that the mechanisms proposed, evolutionary bottlenecking, ecological clearing, oxygenation pulses, while plausible and consistent with the evidence, are not proven in the way that laboratory chemistry is proven. What can be said with confidence is that the most severe environmental contraction in the history of complex life was followed, in geological terms promptly, by the most significant biological diversification in the history of complex life. The planet that nearly erased itself became, in the deep time accounting that evolutionary biology keeps, the planet that built the conditions for everything that followed. Every animal that has ever lived, every ecosystem that has ever existed in the 540 million years since the Cambrian explosion, traces its biological lineage through a thread that passed through the cryogenian winter and came out the other side carrying whatever genetic information the freeze had left intact. The Earth survived. This fact, stated plainly, risks sounding like comfort, like reassurance that no matter what happens to a planet, it recovers, that the system is resilient enough to absorb any perturbation and return, eventually, to something capable of sustaining life. And in the deepest geological sense, the cryogenian story does demonstrate exactly that. The planet survived total freeze. It survived through volcanic persistence, through the patient, million-year accumulation of carbon dioxide in an atmosphere that had no way to draw it down, through the tectonic restlessness of a planet that cannot stop exhaling regardless of what its surface is doing. It survived through biological tenacity, through the irreducible stubbornness of microbial life in hydrothermal darkness, holding the thread of chemistry and reproduction across an epoch that eliminated everything else. The feedback loops that nearly destroyed the planet were eventually counteracted by other feedback loops. The thermostat regained its leverage, and a world that had been a white mirror of reflected light became, again, a world of open water and photosynthesis and biological possibility. But the geological thermostat that rescued the planet operated on timescales measured in millions of years. The volcanic accumulation of sufficient carbon dioxide to overcome the albedo feedback of a fully glaciated planet required tens of millions of years of patient outgassing against a surface that resisted every degree of warming it delivered. The weathering thermostat that then dismantled the post-glacial super greenhouse required millions of additional years of chemical reaction between acidic rain and exposed silicate rock. The biological recovery that followed required tens of millions of years more before anything resembling ecological complexity reappeared. The planet survived, but it survived slowly, on geological time, with a patience that has no human analog and requires no human participation. The climate shifts unfolding today are not geological in their pace. They are not being driven by the slow accumulation of volcanic outgassing across millions of years of sealed ice cover. They are occurring across decades, timescales at which the geological thermostat is essentially motionless, at which silicate weathering cannot respond, at which the feedback loops that operate on million-year cycles have not even registered the perturbation yet. The Earth will, eventually and certainly, absorb whatever happens to its atmosphere in the next century and correct for it across the subsequent millions of years. The planet is not fragile in the deep time sense. Life in some form will persist, but the version of Earth that sustains the particular conditions under which human civilization exists, the 10,000-year window of extraordinary climatic stability that made agriculture possible, that made cities possible, that made the entire accumulated structure of human experience possible. That version is not guaranteed by the planet's long-term resilience. It is a specific configuration produced by a specific set of conditions maintained by feedback loops operating within ranges that Snowball Earth demonstrated, with geological finality, are not inviolable. The planet survived the ice. The question the ice leaves behind, for a species that can read the rock record and understand what it is saying, is not whether Earth will survive what comes next. It will. It always has. The question is narrower and more personal, and considerably more urgent. Which version of Earth survives, and who or what is present to inherit it?